Okay, here we go. Talking a little bit now about electrode potentials. Electrode potentials. So, in order to kick off that discussion, let's just start by just really quickly reiterating what a redox reaction is. Just refreshing our memories, if we can, on redox reactions. Woohoo! Okay, so what is an oxidation number? That is right. I'm just going to assume you guys all answered that out loud and answered it correctly. One can hope, right? An oxidation number, as we've talked about in class and in previous videos, is simply the state that describes the electrons that are accepted or donated in an overall bond. So it's a way of describing how electrons are shared in a bond. Like so, right? So redox reactions, right? Redox reactions are essentially reactions in which atoms lose or gain electrons as new bonds are formed. And again, hopefully none of this is new information for you. It's just good to have that in our minds as we move forward. So we've used a couple of different mnemonic devices, the Leo, the line, says Gur. In this today I'm going to use one called oil rig as a way of keeping our terminology straight. We say that when something is oxidized, we say that oxidation is electron loss, is losing an electron, right? Oil as an oxidation is loss. Rig, on the other hand, reduction is electron gain, which of course you already knew, right? So let's put this all in context. I know this is all very hand wavy at the moment. Let's say I've got some solid iron. And I've got some hydrochloric acid, some hydrogen chloride. So if I react those two things together, I might end up with iron chloride and some hydrogen gas, right? Now, in order to get there, if we were just to look at the, again, oxidation numbers, the original oxidation numbers here, I'd say, okay, well, iron, of course, is not bonded with anything. It's just hanging out, so its oxidation number is 0, right? Because it's neutral. In the hydrogen chloride, on the other hand, right, remember these two are sharing. So right now, hydrogen is +1 and chloride is -1, and they're kind of balancing each other out. So in other words, chlorine, which as we all know is a very greedy a greedy element, right? That really, really wants to be a noble gas but isn't quite, right? It's a halogen. It is essentially snatching hydrogen's electron and leaving it with a slightly positive charge. Okay, by the time we get over here, though, right, notice that's what's happened is we've got a -2 charge on the chlorine, right? Which means that iron has to have acquired a +2 charge. And then now this guy over here, now the hydrogen gas is neutral, right? So we've had essentially two different things just happen, right? On the one hand, we've got the iron, which went from being neutral, no charge, to a +2 charge. So it, in other words, lost electrons. It lost electrons along the way, which, again, we think of as oxidation. So iron was oxidized. And if we wanted a more kind of precise way to say that, we could use what's called a half reaction. A half reaction. So I could essentially say, okay, in order to better explain or to better show this oxidation, I'm going to use this half reaction. I started off with straight up iron, and after that reacted, I got iron with a +2 charge and a couple of electrons floating free, right? And again, this is what's called a half reaction. Okay, but that's not the only change that's happening in this reaction that we just talked about. Certainly there's more than one thing happening here. And the other thing that's happening, here, let me pick a different color. The other thing that's happening here is hydrogen is going from being a +1 charge to being neutral, right? So we also have, so I'm going to write that down. So it's essentially gaining electrons, right? So hydrogen was reduced, right? So if I wanted to come up with a half reaction for this reduction, I might say I started off with these two hydrogen cations, and then along came these two free electrons, and hydrogen snatches them up, and before you know it, you got neutral hydrogen gas. See how that works? So these are also what are sometimes referred to as ion-electron equations. Ion-electron equations. And they're going to be useful in our discussion of electrode potentials today. I promise I'm going somewhere with this. I promise, guys. Okay. So, galvanic cells. Galvanic cells. You guys have already heard quite a bit about these over the course of the various podcasts. So I'm going to try not to talk your ear off about them too much, right? But hopefully one of the things that you remember about galvanic cells is that they generally have a cathode and an anode. Which sort of exchange electrons between the two, right? And the cathode is always the thing where the reduction is taking place. And the anode is always this thing where the oxidation is taking place, which means that the reaction that is causing a galvanic cell to happen, essentially, when we think of a battery, what's really happening inside that battery is a redox reaction, right? Is a redox reaction. Any reaction like this one that I have here is a redox reaction because we've essentially got electrons, atoms losing or gaining electrons as they're switching teams, essentially, as they're forming new bonds, right? So this is sort of, by its very nature, a redox reaction. And we already know that when we say something is reduced, what we really mean is that we've got electrons gained. We're gaining electrons. And when we say something's oxidized, we mean we are losing electrons. So in that original example that Sal Khan uses, and it's not just Sal Khan, it's a very famous example. A lot of people use it. But essentially, the place where you would have seen this before is in copper and in zinc. You might have noticed about this sort of annotation I'm using. This is a pretty common way to see galvanic cells sort of indicated, where this is always going to be the cathode and this is always going to be the anode. It's just kind of a nice shorthand method to use for when you're feeling lazy and you don't have to explain exactly how your battery works to every passing human being, you know. So that is useful. So in the standard copper zinc, galvanic cell that we've been talking so much about in the past couple of videos, if we were to do a half reaction or a series of half reactions here for this, it would probably look a little something like this. You've got your copper ions, cations, right, that are gaining a couple of electrons, and that's giving us solid copper, CuS. Right, and then you've got your zinc, your solid zinc, where a couple of electrons are popping off, leaving you with a zinc cation, right? So this is just another example of half reactions for like a pretty basic standard galvanic cell, right? Okay, so now to get to sort of the point of today's lecture, to get to the point, electrode potentials, right? Electrode potentials. So essentially when we talk about these, we're talking about the energy required to move electrons from metallic atoms to remove electrons from metallic atoms. And you'll oftentimes see this annotated as, essentially like this, right? And the little O up at the top, by the way, just means that we're sort of assuming standard conditions. So, 25 degrees Celsius, 1 molar, and this will be measured in standard voltage. Measured in standard voltage. So electrode potentials, essentially the energy that we would need to remove electrons from metallic atoms. Oops. And it just so happens, convenient, I know, that I have a little chart right here of a couple of pretty typical standard reduction potentials, right? So when we talk about reduction potentials, we essentially just mean if in the redox reaction this is what's being reduced, right, then this is the voltage required to make that happen, right? Now, because these are reduction potentials, right, if we want to talk about oxidation potentials, essentially what you have to do to this chart below is you have to reverse the charge. Reverse the charge. So essentially, if I want to oxidize iron instead of reducing it, right, this would go from being positive 2.87 to being negative 2.87. So yeah, essentially, if you want to talk about oxidation rather than reduction, the only change is you just need to reverse the charge of whatever number you're talking about. Okay, hopefully that kind of makes sense. And the reason we care about electrode potentials, the reason this matters, is because they will essentially tell you what reactions will occur and how readily they will occur. So these numbers will tell you what reactions will occur and how readily they will occur, which is pretty neat. So I know, again, that's all very abstract right now, so let's try an actual example. Actual, real live example. Okay, how about, yeah, I think a nice bright orange would work really well here. Okay, let's say I've got some magnesium. Just like a solid magnesium strip. And let's say I combine that with some chlorine gas. Okay, so let's think a little bit about what the oxidation numbers are right now. Obviously, they're both neutral, right? So it's +0 and +0. When they combine, however, this is a pretty basic combination reaction. When I look at these numbers again, now the oxidation number on chlorine is going to be -2, and the oxidation number on magnesium is going to be +2, right? So if we were to look at this in terms of the half reaction that's occurring, in terms of the half reaction, I might say, okay, so I'm starting off with some magnesium, and then looks like a couple of electrons are popping off of my magnesium to form an ion. Now I got some electrons floating around. On the other hand, right, for chlorine, what appears to be happening is that I had some gas just minding its own business, and it came across these two little electrons and said, okay, so we're going to break apart from each other. We're each going to steal an electron, and that way we can both pretend that we are noble gases separately from each other. And that's going to give me 2 chlorine anions, right? Okay, so again, magnesium in this case, what? Is it being reduced or is it being oxidized? Is it gaining electrons or is it losing electrons? That is absolutely right. It is losing electrons. We know from our little mnemonic device, oil rig, right, that if you lose electrons, that is oxidation. That is oxidation. And chlorine, is it losing electrons or is it gaining electrons? That's right. It's gaining electrons, right? We know from oil rig that that's what's called reduction. So now, if we turn our attention to this magical chart which we found, this fantastic chart which we have at our disposal. We look at, say, magnesium, which, remember, it's being oxidized. Let's see. I don't know. Is magnesium on my list here? So magnesium might not be on this list. I apologize. I was so proud of myself. Oh, here it is. Haha. Took me a minute, but I found it. So this is the reduction potential of magnesium, right? Now remember, we're talking about oxidation. So we're essentially going to take this number, we're going to change the charge on it. So if the reduction is negative 2.37, then the oxidation will be positive 2.8 or 37 rather. 37, right? So if I take that information back up here, I might say, okay, for this half reaction, my electrode potential is positive 2.37. Okay, so chlorine is reduction. So I look down my list. Chlorine. Aha! There it is. Silly Katie, it was right up top. And we see that its potential is 1.36. 1.36. So if we combine these two numbers, we're going to get what's called the net electrode potential. And that is, in this case, going to be what? Positive 3.73. So a positive number, by the way, for electrode potential means that the reactions happen spontaneously. The reactions happen, spontaneously. And the other thing that I want you guys to know about a galvanic cell, and I'm hoping that you pick this up from the cell con lectures, but just in case it wasn't already kind of evident to you that this is the case, one of the interesting things about galvanic cells is that in these, redox reactions do in fact occur naturally. occur naturally. So finding that this has a positive number for its net is pretty much as good as telling me that the reaction will occur in a galvanic cell. Okay, so let's go ahead and try a couple of practice problems together. Okay, so again, all of these are just standardized testing practice problems. Par for the course, yeah. So let's start with this one here, the top one. A galvanic cell is set to operate at standard conditions. Okay, so that's pretty much just like, them covering their bases, right? If it's made of magnesium and the other is made of copper, then the magnesium electrode will serve as and then they're asking you essentially, is it the anode or is it the cathode, right? Now, first off, let's be clear. We talked about this up here. The cathode, right, is the thing that reduces, and the anode is the thing that oxidizes. So do you guys see anything we can eliminate immediately? Yeah, that's right. For instance, B, you can't be the anode and be the site of reduction. If you're the anode, you are by definition the site of oxidation, so we can get rid of that. You're right, C. So cathode, by definition, is the site of reduction. It cannot be the site of oxidation, so we can get rid of that. So now we're just left with either A or D, but it's still, a ways from answering our question. So in order to answer this, it'll probably be helpful if we go take a look at magnesium and at copper on our little charts. So we already found magnesium, woohoo, which is this guy, right? And let's find copper if we can. Aha. So there's this guy, copper. Now notice, again, we learned earlier that positive numbers for reduction potentials mean that the reactions happen spontaneously, right? So a negative number means that it wouldn't happen spontaneously. So in other words, magnesium does not reduce spontaneously. It does not reduce spontaneously without some encouragement. On the other hand, copper, it would appear, does reduce spontaneously. So in a galvanic cell, it would make sense that copper would essentially take the role of the thing being reduced, and magnesium would take the role of the thing being oxidized, right? And that would mean that magnesium would be the anode and the site of oxidation, or answer choice A. Fabulous. Okay, so let's take a look at the second guy. What is the standard cell voltage for the reduction of an Ag cation by Al, right? Remember, Ag is the silver symbol and Al is aluminum, so this would be the silver cation getting reduced by Al. Now remember, when we say silver is getting reduced, we mean Rig. Remember, it is gaining an electron. It is gaining an electron. So if we were to, write out a couple of half reactions here, we might find, for instance, that Ag plus, right, would gain an electron to become neutral. Oops, sorry. AgAl. This is Ag. Ag. Okay, and if we look at our little chart here, we see, aha. In that case, that would be an energy of 0.8. So the reduction potential would be 0.8 0.8. Okay, so looking at aluminum, where are you at, aluminum? Aha! Now notice, here's aluminum. And remember, aluminum in this case is going to be oxidizing as opposed to reducing. So instead of doing negative 1.66, here would be doing positive. So for aluminum, I won't bother to write out the whole reaction because it's not necessary for this problem. Be positive 1.66, right? So then the net voltage is just these two electrode potentials added up together, right? So that gives you what? 6. So 2.46, if I've done my math correctly. All right, beautiful. So that's your answer. Woohoo! Okay, final example. For the reaction below, I should say, which of the following statements is true? So looks like they want to know whether or not the reaction is spontaneous. And notice again, there's a couple that you can eliminate here just based on common sense. We know that if a reaction is spontaneous, its cell voltage must be positive. So B can't be right because you can't have a cell voltage be negative and have the reaction be spontaneous. It doesn't work like that. And then not spontaneous because its cell voltage is positive also would not work here, right? Either it's spontaneous because it's positive or it's not spontaneous because it's negative. Nothing else makes sense. So we can at least get it down to A or D. Okay, so now let's try to actually work out the problem. We know we're dealing with Au, that's gold, and iron, right? Au and iron, or Au and Fe. So in this case, the first question is which one of these is being oxidized and which is being reduced, right? Well, it looks to me like gold is losing a good 3 electrons, right? So it looks to me, again, remember oil, oxidation is loss, right? Like this guy's being oxidized, and that would mean iron is being reduced. So if we look over here, okay, so Au, like reduction of Au is 1.50. So that would mean oxidized, right? It would be the opposite charge. So it'd be negative 1.5. Okay, so the reduction potential of iron, here we go, is 0.77. Is what it looks like to me. 0.77. So that's going to end up being a negative charge. And as we already know, if it's a negative charge, that means that the reaction is not spontaneous, and that means D is our answer. Fantastic. Okay, so thanks for bearing with me, and I will see you in the next video. I am looking forward to it.